I'm Ilija Vukorep. I'm chair of digital design methods in Cottbus in Germany, and together with Rolf Starke, who's here also in audience, and with University of Tokyo, it's a Yasushi Ikeda lab in Tokyo, and Nicolas, Rogeau, and Arastoo, Khajehee, we did this research, and it's about GPU accelerated collision-free path planning for multi-axis robots in construction automation. Collision-free, that's the same thing what we had before. How do we avoid obstacles? And so we all know AEC industries need, in fact, automation, and this is really a kind of a problematic thing. And we hope to navigate this problem with the robotics and to boost our production in AEC. It's really a kind of a critical thing. And one of the quite big problems here is the collision-free path planning. This is something that really all robots, in fact, all machines on construction sites really always are dealing with. And not only on the site, but on the construction site, but also in prefabrication or everywhere we deal with building. So, so the limitations are, in fact, of our current tools is that we don't have these automatically inside of our controlling software. When I talk about this, we have ROS and we have Move It. Move It has got one, but it's not perfect. We all deal with ROS. We all deal with, I don't know if everybody knows it, Grasshopper. In Rhino, with something that we in architectural industry, let's say, we use quite a lot to run machines and run robots. What we built our research on is the research from NVIDIA, in fact, and they developed a framework called cuRobo. And you see two videos of NVIDIA, what they did, and this framework, in fact, enables real-time collision-free robotic motion between 2 points, like between start and the goal point. So you have a kind of you have a room, you have a robot, for example, this, and this is the idea here is from here to here, the movement should avoid these elements what's in the world. So this is the goal, and that's what we see here in the first video. Let me just press here. Maybe we can see. Okay, in the second video, we see here even a moving obstacle. Yeah, it's a person that is then transformed into voxels, and this software, in fact, really working quite good with avoiding this voxels. Or in the second video, you see super quickly movement from A to B and avoiding this part out. Yeah, so this is something that we have, in fact, now. So this is there, and we just have it, but it's not. In fact, it's quite complex to use it because it's on ROS, and we don't want to use ROS for industry, to be honest. We use it mostly in production. We use other tools, yeah, so Move It or let's say Grasshopper and Rhino. And this was our goal, how we can connect these two things. So what we installed was a server that is it's a Linux, it's a Debian computer that is, it's on our faculty somewhere in the rack, and it is running this cuRobo software, and it's getting, in fact, information from the user, from the client. And the client could be any computer that is having Rhino, and the communication works over MQTT. MQTT is a very, very simple communication protocol in real time, but that's important. And we send them from the client, sending the world, let's say a modeled world of this area as a YAML file to the server, and also the start and the end position of the movement. And the cuRobo, in fact, then calculates this and gives this information back to us. And also, what it's very important it's possible to have a dynamic environment here. So this is our lab setup that we just tested for this. We are staking here some we call it a bonsai tree that's coming from the University of Tokyo. And these elements are going to be built up here, and you see a lot of things here. We have a wall here. We have the robot. That is also the collision with itself is a problem. We have like tables, really super complex thing, and we model it all in Rhino. And So it's going to take the stick and put it somewhere here on this area without hitting it. Yeah. You will see little cracks in the video because we had the wrong URDF model of the robot. Now this is UR10, but in the model it's UR10E. So there's like 1.5 centimeter difference in the robot. So you will see some problems here, but doesn't matter. And what is that it's good now here. We have to use it because the calibration didn't work quite good. But it showed really perfectly that the movement really works quite good without affecting, without colliding with any elements here. And this is working really in speed time. So it's really the calculation of the parts is around under 50 milliseconds, and in fact the bottleneck of the whole system is in fact MQTT, the communication, and in fact all these visualization in Rhino and Grasshopper. So this is something that's going slow. So it's the same like in wheelchair. Maybe we need an improvement. We don't want to give the robot whole control of everything. So what we want to show me, please, the path. Yeah, this is all the possible paths that we get from the cuRobo. And then we say, okay, this part we're going to take, and then we press a button, and then the robot takes the joints, the joint numbers here, and then do the movement. So this is something that we did. Then we did a component in Grasshopper that is in fact visualizing and helping the user, the client, to communicate with the very complex software of NVIDIA, of cuRobo, and also all the prototyping things when we have it in robotics, we have a lot of waypoints and so on. Also the support of attachment and detachment is something that you have. For example, if you take an object, you grab it, then it's not part of the world anymore. So it's not an obstacle, and all these things are in fact inside of this component. This was all based on a research funded by DFG, this German funding community that funded also this work with Tokyo. We have also a synchronized setup in Tokyo and Cottbus, and it worked super well. So the overall average response time was 1/4 of a second, was really super good. And it's better than Move It. It's quicker and it's reliable. When we talk about obstacles, and we got a smooth integration with Grasshopper. So it's like something that was not there before. Still, we need some hardware software refinements. And we need to expand robot model compatibility. So we are now building an UFD importer for Grasshopper, and this all will be open source. So this is something that everybody can use. And in the end, what is it? Not easy because you have to install it somewhere on the server. Still the other software. So, but still the communication with Grasshopper will work quite good. And yeah, if there are any questions, I would be glad to answer you.